Dear my students, I am greeting you. As we said, we will probably give our lectures on the internet until the end of the coronavirus pandemic. So we continue our lecture. Doctor of Chemical Sciences, Associate Professor Zulmatar Baliyeva, Department Biophysical and Bioorganic Chemistry of Azerbaijan Medical University. Today we will talk about the basic notions and laws of chemical thermodynamics and bioenergetics, application of the first law of thermochemistry to the biological systems, statistical nature of entropy, Gibbs Free Energy, thermodynamics of the irreversible processes. First of all, I want to remember you many different forms of energy: kinetic, internal, potential, mechanical, chemical, electrical, and you know that energy cannot be created, not destroyed. And here you see internal energy is equal to kinetic and plus potential energy of the molecules or atoms of body, and kinetic energy is equal to translation, rotation, vibration of the molecules or atoms, and for energy equation you see here. Then add the units of energy. So you know SI units for energy is a joule, and sometimes the calorie is used instead of the joule. And how can we calculate it? Joule, you see, from this equation. Now about theoretical of thermodynamic or theory of thermodynamic. Thermodynamics appeared at the end of the 18th century in connection with the necessity of the creation of a theory of the heat engines. Thermodynamics for Kriegson and dynamic heat and motions. Thermodynamics said the transition of energy from one form to another one. Energy effects accompanied by the physical and chemical processes, possibility, direction and scope of the spontaneous processes running, and the conditions of the chemical equilibrium as well. The biological systems are defined by an exclusive ability to convert mechanical, chemical, and electrical energy, energy of light, and even energy of the magnetic field to each other. It is a city of understanding the thermodynamics in medicine and biologic fields from a desire to explain the energy conversions in the biological system. Therefore, biological thermodynamics is called bioenergetics as well. Bioenergetics studies a mechanism of the transformation of energy in the cells. The main kinds of work in the living cells are electrical and chemical, which are performed with the participation of the biological membranes. Beginning with clones, muscle contraction, up to protein biosynthesis, all processes demand energy. Adenosine triphosphate, ATP, hydrolysis of which ensures the organism with required energy is a donor of energy in the living organisms. The following serve those terms to which it's necessary to give a clear definition is used in thermodynamics. Temperature. Temperature is a measure of the intensity of the heat motions of the atoms and the molecules. Heat is a chaotic motions of the atoms and molecules, constituting a macroscopic fixed body. Energy. Energy is a measure of the matter, motion, or an ability to perform work. A body or a group of bodies which are in interaction and are isolated from the environment by a real or imaginary shell is called a system. Some important properties depend on the properties of this boundary. A system is called thermodynamic if mass and heat exchanges are performed between all its constituents in it. Independence on a character of the interaction with environment, the thermodynamic systems are subdivided into open, closed, and isolated ones. If a system exchanges its mass and energy with environment, then it's called open. If a system exchanges with environment only energy in the form of heat and work, then such system is called closed. If between the system and the environment mass and heat exchanges are lack, then such system is called isolated. A system consisting of the one phase is called homogeneous, and if a system has several phases, it's termed heterogeneous. A state of the system is a complex of the physical and chemical properties characterizing the given system. A state of the system is characterized by thermodynamic parameters such as pressure, volume, temperature, concentration, and so on. The properties of a system determining its state are divided on the intensive, which do not depend on mass, and the extensive, which depend on mass. Intensive properties include temperature, pressure, concentration, density, chemical potential, and so on. And the extensive properties include volume, mass, internal energy, enthalpy, entropy, thermodynamic potentials, heat capacity, and so on. Changing of any thermodynamic parameter of the system is called a thermodynamic process. There are the following types of the processes: isothermic, isobaric, and isochoric processes. You know from school, isothermic processes, temperature is equal to constant, and in isobaric processes, pressure is equal to constant, and isochoric processes, volume is equal to constant. If changing of the parameter depends on the initial and the final states of the system and doesn't depend on the process way, then such parameters is called a state function. The thermodynamic processes can be both reversible and irreversible. A reversible process is a process which can be returned to the initial state without any energy changes in environment and the system. An irreversible process is a process after flowing of which it's impossible to return the system and environment to the initial state. In irreversible processes, the system changes in such a way that the system and surroundings can be put back in their original states by exactly reversing the process. And changes are infinitesimally small in irreversible processes. And irreversible processes cannot be undone by exactly reversing the change to the system. All spontaneous processes are irreversible, and all real processes are irreversible. Now about entropy. Entropy is a term coined by Rudolf Clausius in the 19th century. Clausius was convinced of the significance of the ratio of feed delivered and the temperature at which it's delivered. Entropy can be thought of as a measure of the randomness of a system. It's related to the various modes of motion in molecules. Entropy, like total energy E and enthalpy H, entropy is a state function, therefore delta S is equal to S final minus S initial. For a process occurring at constant temperature and isothermal processes, delta S is equal to Q ref divided by 2 T. Q ref the heat that is transferred when the process is carried out reversibly at a constant temperature, and T is temperature in Kelvin. Thermodynamics is based on three laws. They are empirical laws which are established on the basis of the different experiment, observations, or simply from a common sense. They do not have a theoretical justification, and they themselves are that foundation on which theoretical thermodynamics stands. The first law of thermodynamics is a law of energy conservation. More accurately, upon consideration of E is equal to mc square, a law of energy and mass conservation. First, this law was stated by Helmholtz. If any process occurs in an isolated system, then a total energy of the system remains invariable. In a system which exchanges by heat with environment, an absorbed heat is consumed for changing the system energy and performing work. The first law of thermodynamics is an expression of the principle of conservation of energy. The law states that energy can be transformed. It changed from one form to another, but cannot be created, not destroyed. It's usually formulated by stating that the change in the internal energy of a system is equal to the amount of heat supplied to the system minus the amount of work performed by the system on its surroundings. For the infinitely small change, the mechanical expression of the first law of thermodynamics. The first law of thermodynamics is great importance for calculation of heat effect. This division of thermodynamics is called thermochemistry. As a rule, chemical reactions are accompanied by heat effect. The chemical equations in which heat effects are indicated are called thermochemical ones. The reactions which occur with heat liberation are called exothermic, and with heat absorption, endothermic reaction. Exothermic reactions are accompanied by a positive thermal effect Q more than 0, and endothermic reactions by negative thermal effect Q less than 0. In thermodynamics, a reverse system of the signs is accepted. A thermal effect of endothermic reaction is connected with increase of enthalpy of the system, delta H, and thermal effect of the exothermic reaction is related with its decreasing. Exothermic and endothermic processes in exothermic processes absorbs heat from the surrounding. An endothermic reaction is called delta H more than 0. And exothermic reactions transfer heat to the surroundings. And exothermic reactions delta H less than 0. And it's called combustion reaction. Heat effect of a reaction is state function and depends only on the initial and final states of system, not on how the internal energy is used. And from this slide you see equation for internal energy and other state functions. At isobaric processes, we can write this equation like this: Qp is equal to delta U plus P delta V, and is equal to this expression. Then, and after introducing of a new function, enthalpy is equal to U plus PV, and Qp is equal to this expression. They, in these conditions, become state functions. The enthalpy H, or heat content of a system, is energy which a system P is equal to constant possesses. Enthalpy is a state function, and it's a convenient value for calculating heat effects of isobaric processes, since majority of biochemical reactions occurs at P is equal to constant. It's impossible to determine an absolute value of U and H. Only their changes, delta U and delta H, can be measured. For exothermic reaction written according to thermochemical system, like this, and thermodynamic system, like this. In order to carry out thermochemical calculation, there was introduced a notion, thermal effect at standard conditions, thermal effect which accompanies a reaction at standard pressure. Standard pressure is equal to 1.013 multiplied 10 power 5 Pascal, and standard temperature is equal to 298. It's called the thermal effect at standard conditions. Standard heat of formation is called the thermal effect of the formation reaction of 1 mole of the substance from the corresponding separate elements taken as the form of the stable aggregative state at standard pressure. Standard heat of formation is symbolized by delta H 0 F 298. Where upper index 0 shows standard conditions, lower index F its first letter of formation. And standard heat of combustion is called the thermal effect of the reaction in which 1 mole of the substance is burned in oxygen at standard pressure. Standard heat of combustion is symbolized by where lower index is C is the first letter from combustion. At thermochemical and thermodynamic calculations, as a rule, molar heat capacities of bodies are used. Molar heat capacity is an amount of heat which is needed for heating 1 mole of substance by 1 Kelvin and is expressed by formula this. Suppose we have determined delta H for a reaction at temperature T1 and we want delta H0 at T2. Differentiation of delta H0 and delta U0 partial derivatives with respect to temperature at constant pressure isobaric process and constant volume isobaric process respectively gives this equation. And where Cp and Cv, delta Cp and delta Cv, are molar heat capacity changes of the processes at constant pressure and constant volume. These equations are called Kirchhoff's equations. Integration of Kirchhoff's equation between the limits T1, T2 allows to calculate thermal effect delta H2 of processes at T2 where pressure is equal to constant. If thermal effect of processes delta H1 and delta T1 is known. And analogous expression is obtained for the thermal effect of the processes at V is equal to constant. Laplace's law first and Hess law second constitute a basis of thermochemistry. According to the first law of thermochemistry, during formation of a substance, heat is liberated or absorbed as much as it's absorbed liberated at its decomposition. The second law was discovered by Russian scientist Hess, who established that a thermal effect of a reaction doesn't depend on a process way, but it's determined only by initial and final states of the system. Hess law can be shown by the following example, like this. A formation of the reaction product carbon dioxide represented by two ways. By an immediate formation of carbon dioxide from the initial substance carbon first, and through a formation of the intermediate compound carbon monoxide, according to the Hess law, not depending on a preparation way of the reaction product, a total thermal effect for all reactions will be the same. I delta H is equal to delta H1 plus delta H2. A thermal effect, a reaction under the standard condition, is equal to difference between sums of the formation heats of the final reaction products and the initial products multiplied by the appropriate stoichiometric coefficients. A thermal effect of a reaction under the standard condition is equal to a difference between sums of the combustion heats of the initial products and the final reaction products multiplied by the appropriate stoichiometric coefficients. Thus, thermal effects of different physico-chemical processes, for example, neutralization, dissolution, hydration, and so on, can be calculated on the basis of Hess laws. They may be determined experimentally by means of calorimeters. The second law of thermodynamics: the entropy of the universe doesn't change for reversible processes and increases for spontaneous processes. Reversible processes, delta S universe is equal to delta S system and plus delta S surroundings is equal to 0. And irreversible processes, this process is real and spontaneous. And in irreversible processes, delta S universe is equal to delta S system and plus delta S surrounding more than 0. And the entropy of the universe increases real spontaneous processes, but entropy can be decreased for individual systems. Reversible processes in ideal gas as delta S universe is equal to delta S system plus delta S surrounding is equal to 0, and irreversible real spontaneous processes S universe is equal to delta S system is equal plus delta S surroundings more than 0. Energy is needed for growing and functioning of all living organisms. The living organisms gain this energy at the expense of oxidation of the nutrients. In order to show an applicability of the first law, it's important to prove the following. In the first place, an organism is not a source of a new energy. In the second place, all kinds of work are executed by an organism at the expense of energy liberated during oxidation of the nutrients. For this reason, the methods of direct measurement of an expenditure of energy and indirect calorimetries are used. In the latter case, an expenditure of energy is determined on the basis of the respiratory coefficients and the caloric coefficients of oxygen. A respiratory coefficient is a ratio of the volumes of liberated carbon dioxide and absorbed oxygen for carbohydrates, proteins and fats is 1.0, 0.85 and 0.71 respectively. A caloric coefficient of oxygen is a quantity of heat which is liberated at utilization of 1 liter of oxygen. For carbohydrates, proteins, and fats is 21.2, 20.1, and 19.6 kilojoule respectively. Comparison of the results obtained by these methods shows that energy balance coincides and accurately within 1-3%. It points to execution of all kinds of work only at the expense of oxidation energy in the nutrients. A required store of energy in the organisms is accumulated in the high energy bonds of the different phosphorus containing compounds, ATP, acetic phosphate, phosphoglycerates, and so on. Upon hydrolysis and synthesis of these compounds, a definite quantity of energy is demanded. Energy included into these bonds is consumed on a construction of the cells, synthesis of the proteins, polysaccharides, mechanical work of the muscles, the heart, and so on. Thus, the first law of thermodynamics is a law of conservation of energy and helps at the calculations of energy balance of the processes. However, the fourth law of thermodynamics doesn't say whether any event will occur and in which direction the changes may run. The second law of thermodynamics deals with this question. A direction and boundary of the processes occurring is determined by the second law of thermodynamics. According to this law, it's needed to introduce one function, value of which defines the process occurrence in the given direction. Such function, by the suggestion of Clausius, was called entropy. A postulate about entropy existence is one of the formulations of the second law of thermodynamics. Heat and work are transit forms of energy. However, if they were converted to each other to the same extent, there would be no difference between them. But such difference exists. Work is completely converted to heat, but heat is transformed to work only partially. The rest part of heat is dissipated, i.e. is transmitted to environment. Therefore, natural processes proceed irreversibly, except superfluidity and superconductivity, and in one direction. So, heat is never transmitted from cold body to hot one. It's another formulation of the second law, and such a transition is always an inverse because a part of heat is always transmitted to environment. For example, a kettle on the stove and the room. The following formulation of the second law states it's impossible to construct a periodically working device which would convert heat to work without a change in environment, i.e. without compensation. It's impossible to convert heat completely into work. Thus, the second law of thermodynamics establishes the borders of the heat conversion into work. In order to understand the role of entropy in determination of the direction of the processes, let's consider an experiment. Assume there are two vessels. In one of them, pressure of the gas is more than in another one. A system as a whole is isolated, i.e. isothermic. If the tap is opened, then gas flows from left to right. However, a sum energy of the two vessels is constant, is not changed. Nevertheless, as the equalization of pressure occurs, therefore, a process behavior is determined by some few new functions, not by energy. Entropy is this function since upon equalization of the density just entropy is changed. Another theoretical question of thermodynamics is connected with entropy. From current cycle, on which the work of the heat engine is based, follows that the coefficient of efficiency is determined. As efficiency is equal to Q1 minus Q2 divided by Q1 and is equal to T1 minus T2 divided by T1. And Q1 and Q2 are heats respectively given to the system and lost by its. T1 and T2 are respectively temperatures of heater and cooler. So heat is proportional to temperature, i.e. Q approximately is equal to T, temperature. However, in order to put a sign of equality between them, a new function is needed, i.e. as a constant of proportionality. It turns out that entropy is this functions, i.e. delta Q is equal to T delta S, or this equation. Therefore, S is called a heat coordinate of a system, and execution of this relation is a postulate of thermodynamics. A sign of equality in this equation is related to reversible processes, and for irreversible processes, d is more than dq divided by t. Therefore, in a general case, this equation form. And this equation has an important consequence. If in an isolated system, the Q is equal to 0, a reversible process occurs, then entropy is equal to 0 and entropy is constant. In the case of running of irreversible processes, entropy is increased. Entropy is a state function as well. However, is in contrast to U and H, its absolute value can be determined. The third law of thermodynamics deals with this question. A formulation of the given law is Nernst thermal theorem. Chemical reactions at absolute zero proceed without changing of any entropy. And Planck supplemented this theorem by the following postulates. Entropy of the ideal chemically individual substance at absolute zero is equal to 0. A magnitude of Planck's postulates consists in that the calculation of entropy for some temperatures is performed by the formulas, where S0 and St, entropy of substance at absolute zero at temperature T respectively, and this equation form. It's needed to know the value of S0 to this effect. A question arises here with, what meaning does entropy have at absolute zero? In order to answer this question, it should be noted that, as compared with the fourth law, the second one has a more restricted application. It's only applied to reversible processes and to the systems which consist of a great number of the particles. Such systems are described by mechanics laws and the theory of relativity. So the second law of thermodynamics has a statistical character. It's observed only if a great number of the events are considered. This implies that a certain connection between entropy and probability must be realized. It was established by Boltzmann, who showed that entropy can be considered as a measure of thermodynamic probability, W, of the system, where K is Boltzmann constant. And thermodynamic probability is a number of the microstates by means of which it's possible to realize the given macrostates of the system, i.e. the same macrostate given by the thermodynamic parameters can be performed at the different distribution of the energy among separate molecules, where n and n number of molecules situated in the cells. And you see in this picture scheme presented for a calculation of the thermodynamic probability demonstrating a distribution of the particles in the cells. The fact that W is increased in the spontaneous processes and reaches a maximum at equilibrium makes entropy an extraordinarily convenient and important quantity. From this point of the view, a spontaneous process in an isolated system proceeds with increase of entropy and at equilibrium when a microscopic irregularity of the system is maximum. Entropy reaches a maximum value as well. Therefore, spontaneous processes always run in the direction from a less probable state to a more probable one. Thus, entropy is a measure of the disarray of the system. Such a conclusion in due time led to a theory called heat death of the universe and discovered by Clausius. According to it, if to consider the universe as an isolated system, then time arrow always will point to a site of increase of entropy in the universe. At the end we come to the state in which differential entropy divided by differential T temperature and equal to 0, i.e. entropy reaches maximum and already there are no events. This theory was further rejected by Boltzmann, Smolkovsky, and others. They showed that an equilibrium state of the universe is never reached because the universe is not static and permanently evolves. At present time, universe is at the stage of an expansion. According to the theory of the primary explosion, the universe first was in the superdense state, and as a result of the primary explosion, the splinters were formed which correspond to the stars and the solar systems, and they were removed from the center with a higher rate. Black hole is a model of such superdense state which absorbs everything and reflects nothing. An expression of the universe cannot be continued endlessly. With the lapse of time, this process is called chaos and an expansion of substituted by a compression. As a result of the compression, death of life occurs and it proceeds until the universe reaches a superdense state. After that, again, a big explosion occurs and everything is repeated. Life arises and then dies, and so endlessly. In this connection, a question arises about time symmetry. Time always goes forward. Is it possible to see that path? With a glance, do that there are black holes, and taking into account an influence of gravitation on time passing, it can be said that hypothetical it's possible. Let's consider that a spaceship and astronaut approaches to a black hole. When approaching to the black hole, in a spaceship time gets decelerated in comparison with time on the Earth, and then the astronaut will see the future of the Earth. Now let's consider that a spaceship is in a black hole. However, it releases nothing, and if it considers with a big explosion, then a spaceship with the splinters will be removed from the center, and therefore it will be possible to see a creation of life, beginning of life. The past will be able to be seen. This is an assumed, a hypothetical experiment. Now the scientists carry out the investigations on modeling of the black holes in the laboratory conditions. In recent years, the scientists studying the universe obtained the series of the interesting result. They suppose that the proportion neutrons and electrons constitute 3–5%. The predicted particles of the unknown nature are 25–30%, and dark matter positive density and negative pressure is approximately 70%. Again, a question arises. Is it possible to return spontaneous processes? It's possible. So, a process of photosynthesis, beginning of life, crystallization from the solutions occurs the decreasing of entropy. Returning of the spontaneous process may be achieved by means of a creation of equivalent or higher desire in another place. For example, in the photosynthesis process, a synthesis of the large and complex molecules, carbohydrates and proteins, are accompanied by increasing of entropy on the sun and at the expense of the nuclear conversions, nuclear fissions. Therefore, in the universe, the decreasing of entropy anywhere, origin of the life, is compensated by increasing of entropy in another place, this of another world. Thus, all the universe may be divided into two parts, a considered system and the whole of the rest world. The second law of thermodynamics requires that as universe is equal to a system and plus its environment, more than zero, where sign of equality is related to the irreversible processes, separately system and its universe may be negative, and their sum can never be less than zero. A skill to predict whether a chemical reaction or biological processes will proceed and in what direction is important both for a chemist and for a biologist. For the open system, such prediction is possible if the values of delta S system and delta S environment they are known. In particle meaning a definition of delta S environment is a very difficult task. Therefore, for determination of spontaneously, such a criterion is needed which would be related only the system and would not take into consideration the environment. Now about living organisms as open systems, application thermodynamics to the biosystems and thermodynamics of the reversible processes. Okay, according to the second law of thermodynamics, entropy is a criterion of the spontaneous running of the processes in the isolated system. In the reversible processes, entropy is constant, and in the irreversible ones, it's increased. In the open systems, to which the living organisms are related, it's important to know delta H system and delta environment, determination of which is particularly difficult. Therefore, a more convenient creation for the spontaneity of the process was proposed by Gibbs and Helmholtz. They suggested new thermodynamic function F is equal to U minus Ts. It's Helmholtz free energy. This function is called isothermic potential. Shortly, isochoric potential or free energy at constant value as well. And G is equal to H minus Ts. It's Gibbs free energy. Function G is equal to H minus Ts is called isothermic potential, shortly isobaric potential or free energy constant pressure as well. F and G are state functions, so only their changing can be determined like this. The processes at which Gibbs energy at constant pressure and at constant temperature, and Helmholtz energy at constant volume and constant temperature are decreased are called exergonic. The processes at which these values are increased are called endergonic. The biochemical processes usually proceed at constant pressure, and therefore it's convenient to use delta G. The properties of G, delta G less than zero exergonic reaction is a condition of the spontaneous flowing of the processes. Delta G is equal to zero corresponds to an equilibrium at delta G more than zero in the ergonic reaction. The reaction doesn't proceed spontaneously. For oxidation of glucose, delta G is equal to minus 2079 kilojoule per mole. The process must be spontaneous, but glucose over a long period of time is kept in the air without any change. In this respect, limitation of thermodynamics is become apparent. So long as it permits to receive the information about the possible direction of the process, but it doesn't affirm anything about the rate of the reaction. Kinetics deals with this question. In the living organisms, both exergonic and endergonic reaction proceeds. A fact that dissipation of energy for organization of the biosystems. The law often confuses biologists. Maybe they do not meet the second law of thermodynamics. It appears that they meet, but these systems have an amazing ability with thermodynamics, doesn't expect and forces. This is a flowing of these conjugate processes in the living organisms. Thus, in the process of the glycolysis, the conversions of glucose into glucose 6-phosphate is the first stage of the glucose oxidation. And in biochemistry, in standard free energy is denoted as G01, power 01. The reaction is endergonic and it cannot proceed in the ordinary conditions. However, it's performed if it's conjugated with the exergonic reaction of ATP hydrolysis. And essential is the fact that the reaction, which is energetically disadvantageous, but is required for metabolism, is realized at the expense of a conjugation with another reaction, in the course of which much free energy is liberated. The above-mentioned example illustrates a great importance of the conjugated reactions in biochemistry. A special enzyme, hexokinase, combines both processes into one. A unique role of ATP in the biological processes is connected with the fact that delta G01 of hydrolysis has a moderate intermediate value. Increasing delta G01 would mean that for ATP synthesis, 36 moles of ATP are synthesized at oxidation of glucose. More energy is required, which is undesirable. And if delta G01 were lower than ATP, would not be able to play its important role as energy source in many conjugated processes. Free energy is connected with a constant of chemical equilibrium. As seen from the equation, delta G plays a role of criterion of the processes following. For gas phase reaction, A plus B, and irreversible processes, C plus D. Here, delta G, standard free energy, at pressure P1 is equal to 1 and P0 is equal to 0, and delta G is equal to delta G01, which is connected with an equilibrium constant. Delta G is equal to this expression. This equation contains all information about the chemical equilibrium and therefore is called the main equation of chemical thermodynamics. Free energy is connected with another state function called the chemical potential. i.e., the chemical potential is energy which is needed for increasing the molecules number by the unit. And the chemical potential is an intensive quantity. A general condition of equilibrium may be noted as. Another property of G is that its derivative with regard to T at P constant gives entropy. And from the equation, delta F is equal to delta U minus T delta S, and delta U is equal to delta F plus T delta S, it seems that delta F is that part of energy which is converted to the useful energy, and T delta S is that part of energy which is dissipated. Thus, if an isolated system increase of entropy is a criterion of the spontaneous running of these processes, then in the open systems decrease of free energy performs such a role. On the other bond, delta G01 or R maximum characterizes the chemical reactivity of the substances and therefore is called chemical affinity. Biological thermodynamics is sometimes used to refer to bioenergetics, the study of energy transformation in the biological sciences. Biological thermodynamics may be defined as the quantitative study of the energy transaction that occurs in and between living organism structures and cells, and of the nature and functions of the chemical processes underlying this transaction. The field of the biological thermodynamics is focused on principles of chemical thermodynamics in biology and biochemistry. Principles covered include the first law of thermodynamics, the second law of thermodynamics, Gibbs Free Energy, statistical thermodynamics, reaction kinetics, and on hypothesis of the origin of life. Present biological thermodynamics concerns itself with the study of internal biological dynamics as ATP hydrolysis, protein stability, DNA binding, and membrane diffusion, enzyme kinetics, and such essential energy control pathways. Now Hess law. Hess law, if a reaction is carried out in a number of steps, delta H for the overall reaction is the sum of delta H for each individual step. For example, this reaction we can show for you. Methane, combustion of methane. And spontaneous processes are those that can proceed without any outside intervention. The gas is in a vessel B will spontaneously effuse into vessel A, but once the gas is in both vessels, it will not spontaneously. Then processes that are spontaneous are at one temperature may be not spontaneous at other temperatures. Above zero, it's spontaneous for ice to melt. Below 0 degrees Celsius, the reverse process is spontaneous. And practical user surroundings and system Gibbs Free Energy. We see minus T delta C universe is defined as the Gibbs Free Energy. For spontaneous processes, delta universe is more than 0, and therefore delta G is less than 0. Delta G is easier to determine than delta is universe. So use delta G to decide if a process is spontaneous. Then Gibbs Free Energy. If delta G is negative, the forward reaction is spontaneous. If delta G is 0, the system is at equilibrium. If delta G is positive, the reaction is spontaneous in the reverse direction. And standard free energies of formation delta G F0 are analogous to standard enthalpies of formation delta H F0. And delta G F0 is equal to this expression. Delta G0 can be looked up in tables or calculated from the C0 and delta H0. And free energy changes its Völke equation, written like this. Equation shows how delta G0 changes with temperature. We assume the S0 and delta H0 are independent of temperature. And free energy equilibrium, under non-standard condition, we need to use delta G instead of delta G0. And we can write like this. Note that equilibrium delta G is equal to 0. Away from equal sign of delta G tells which way reaction goes spontaneously. And thanks for watching and attention.